Hello everyone, this is SMD Mazarullah, Assistant Professor, Deputy Department, IIT Engineering College. I am doing the subject utilization of electrical energy, and today we will discuss about the topic specific energy consumption and some definitions which are very useful regarding the traction movement, as well as we are also study about the mechanics of the train also here, and also some formulas will be discussed. So let's move into the topic with some starting with the definitions. So we'll talk about the basic terms and definitions first. So schedule speed. What is the schedule speed here? Total distances by total time including the stops is called as the schedule speed. And what is the average speed? It is the distance between two stops by running time excluding the stops. Now crest speed also is one of the definition. What is the crest speed? Maximum speed attained by the train during time of run is called as crest speed. That means crest means peak, and trapezoidal speed time curve formula is given here, where it is denoted by some Vm is given, and therefore here alpha beta are some terms that are called alpha is acceleration and beta is the braking retardation. And here we will see that this is Vm is the velocity, that is the maximum velocity. Vm is being calculated by the formula here, and time is in total time of run is in seconds only. And we will calculate about the dead weight. What is a dead weight? It is total weight of train to be propelled by the locomotive, and it is denoted by the letter W. Acceleration weight. What about acceleration weight? It is the effective weight of train that has angular acceleration due to rotational inertia, including the dead weight of the train, and it is denoted by WE. Whereas this accelerating weight is the effective weight of train, which is more than the dead weight, and it is about 5 to 10% of the dead weight actually. Adhesive weight. Coming to the adhesive weight, the total weight of the carried out on the wheels of a locomotive is called as adhesive weight. So it is clear that what is adhesive weight means, it is total weight carried out on the wheels of locomotive is called as adhesive weight. And to define the coefficient of adhesion, it is defined as the ratio of the track to effort required to propel the wheel of a locomotive to adhesive weight. That means that when a wheel should move or to propel, it needs some effort, and the ratio of track to effort to the propel the wheel of a locomotive to the adhesive weight is called as the coefficient of adhesion. Now, talking about the average speed, it is mean of the speeds attained by the train from start to stop is called as the average speed, and it is defined as the ratio of the distance covered by the train between two stops to the total time of run. So it is very clear here that the speeds attained, it is a mean of the speed attained by the train from start to stop. It is defined as the ratio of the distance covered by train between two stops to the total time of run, and it is denoted by VA. V suffix A, where VA is the average speed of train in kilometer per hour, and T is the distance between stops in kilometer, and T is the actual time of run in 5 hours. Okay, this thing we are saying that average speed. And next, coming to this schedule speed. What is schedule speed? Schedule speed is the distance between stops by total time of run plus total time of stop. So here what we see is schedule speed, it is a ratio of distance between stops by total time of run plus time for stop. That is equal to distance between stops by schedule time. Schedule time is nothing but time of run plus time of stop is called as schedule time, and therefore distance between stop is written as it is, and we have schedule speed Vs is equals to d by Ts. Now coming to the schedule speed. What is schedule speed? Definition: the ratio of distance covered between two stops to the total time of run including the time for stop is known as schedule speed. It is denoted by symbol Vs, and Ts is the schedule time in hours. What is scheduled time? It is defined as the sum of time required for actual run and time required for stop. That is Ts is equals to T run plus T stop. Now we will talk about the factors affecting the schedule speed of the train. How the factors that are affecting the schedule speed of the train means, the factors that are affect the schedule speed of train are crest speed, the duration of stops, the distance between the stops, the acceleration, and the braking retardation. So one by one we will see what is that crest speed. Now crest speed, it is the maximum speed of the train which affects the schedule speed or the fixed acceleration or retardation and constant distance between the stops. If the crest speed increases, the actual running time of train also decreases. For low crest speed of train it is running, so the high crest speed of train will increase to its scheduled speed. So it is the maximum speed of train which affects the scheduled speed as per fixed acceleration, retardation and constants between the stops. So crest speed increases, the actual running time of train also decreases here. So we say that speed increase means the time running time decreases. So we are now going to the other one, that is the definition called as duration of stops. What is the duration of stops? If we talk about the duration of stops here, if the duration of stop is more, then the running time of train will be less. So this leads to low schedule speed. Thus for high schedule speeds, a duration of stop must be low. So distance between stop, if the distance between stop is more, then the running time of train is less. You should understand this one. So distance is between the stop is more, and the running time of train is less. Hence the schedule time of train will be more. So these will be the differences between the crest speed, the duration speed and schedule stops. So acceleration, if the acceleration of train increases, then running time of train decreases, provided the distance between stops and crest speed is maintained as constant. Thus, the increase in acceleration will increase the schedule speed. So here we can understand that acceleration will increase the schedule speed. If the acceleration of train increases, then running time of train decreases. And this provided the distance between stops and crest speed is maintained as constant. What is the braking retardation? High braking retardation leads to reduction of running time of the train, and this will cause high schedule speed provided the distance between the stop is small. So what is braking retardation? High braking retardation leads to reduction of running time of train. So these points to be remembered here, and we are having here simplified trapezoidal and quadrilateral speed time curves. So simplified speed time curves give relation between acceleration, retardation, average speed and distance between the stop, which are needed to estimate the performance of service at different schedule speed. So that actual speed time curves for the main urban services are. Now we will talk about the tractive effort. What is the tractive effort? It is the effective force acting on wheel of a locomotive necessary to propel the train is known as tractive effort. So what is tractive effort? It is the effective force acting on the wheel of a locomotive necessary to propel the train is known as the tractive effort, and it is denoted by the symbol F suffix T. The tractive effort or tractive force is a vector quantity always acting tangential to the wheel of locomotive, and it is measured in Newton. The net effective force or the total tractive effort Ft on the wheel of locomotive or train to run on track is equal to the sum of the tractive effort. Now we will talk about the tractive effort here. The required for linear and axial acceleration Fa, and this to overcome the effect of gravity Fg, and to overcome the frictional resistance to motion of the train Fr. This is the thing, that is the net effective force or total tractive effort on the wheel of a locomotive or train to run on track is equal to the sum of the tractive effort. So we see here these things are being discussed here. So mechanics of train movement, the essential driving mechanism here is dealing with this particular mechanics of the train movement. The essential driving mechanism of electric locomotive is shown in this figure given below. The electric locomotive consists of pinion and gear wheel meshed with the traction motor and the wheel of locomotive here. The gear wheel transfers the tractive effort at the edge of the pinion to the driving wheel. So if you see this diagram, you can clearly understand that there are here that wheel is there. The wheel is having some motor armature here upon that, and this motor armature is kept, and therefore the diameter of that armature is small d1 and the diameter of the wheel is d2, and this is called as a motor pinion, and this is called as the gear wheel. And inside the gear wheel the pinion is attached whenever the wheel is moving. Therefore this particular the motor is moving, then the wheel also moves according to the circular motion of this particular motor armature, and this driving wheel also changes upon its speed. So if you want to increase the speed, this gear wheel also changes. When the gears are changed, then the speed also change depending upon the motor circular motion. So this is a track, and this will let you move the wheel with the help of the motor. So driving mechanism of electric locomotives is shown above, and here the torque is also one of the point to be discussed. That T is the torque exerted by motor in Newton meters, and Fb is the tractive effort at the edge of the pinion in Newton, and Ft is the track weight of the wheel, and D is the diameter of the driving wheel. Therefore D1 and D2 are the diameter of pinion and gear wheel respectively, and eta is the efficiency of power transmission for the motor to the driving axle. Now we will have some formulae for this. The torque developed by motor T is equals to Fp into d1 by 2, and here F is equals to 2t by d1 into n. The track to effort at the edge of pinion transferred to the wheel of locomotive is Ft is equals to this Fp into d2 by d into n. Therefore, the total track to effort Ft is equal to eta into, that is efficiency, into 2t by d1 into d2 by d, where d1 is nothing but the diameter of the motor armature, d2 is the diameter of the wheel, and we write here eta into t into 2 by d into d2 by d1, that is eta into t into 2 by capital D into r, where R is d2 by d1, it is known as the gear ratio, and Ft is equals to 2 eta R into T by D into N is nothing but the formula for the tractive effort. The tractive effort required total Ft is equals to Fa plus Fg plus Fr, that is angular acceleration plus force required to overcome gravity plus force required to overcome the resistance of motion leads to the tractive effort. So tractive effort is very important effort in the traction, where Ft is equals to sum of the force required for linear acceleration plus gravity overcome, and this resistance force required to overcome the resistance of motion is called as the tractive effort. Now the force required for linear and angular acceleration is Fa, and according to the fundamental law of acceleration, the force required to accelerate the motion of the body is given by force is equals to mass into acceleration, that F is equals to ma, and let the weight of train be W tons being accelerated alpha is kmph/ps per second. Then the mass of train equation is given like this. The mass of train is 1000 watt per kg, 1000 watt, 1000 W kg, and the acceleration is alpha. Then alpha into 1000 by 3600 meter per second square gives you the acceleration, that is 0.278 alpha meter per second square is the acceleration. So here why? Because we are calculating the acceleration in acceleration means nothing but the mass of train by this seconds, 3600 seconds. Therefore we have discussed about the formula already here. The tractive effort required for linear acceleration is Fa is equals to 1000 W kg, that is nothing but 1000 into W kg is equal to 0.2788 alpha meter per second square. So here 227.88 W alpha kg per meters per second square also we can write here. Okay, so if you want to convert into this Fa, we can do like this. The equation holds good only if the accelerating body has no rotating parts. Owing to the fact that a train has rotating parts such as motor armature, wheels, axles and gear system, hence these parts need to be given angular acceleration. At the same time, the whole train is accelerated in linear direction. The tractive effort required for linear and angular acceleration is given by Ft is equal to 27.88 W alpha n. So tractive effort required to overcome the train resistance. So we will see here tractive effort required to overcome the train resistance. When the train is running at uniform speed on a level track, it has to overcome the opposing force due to surface friction, that is friction at various parts of the rolling stock, the friction at the track, and also due to the wind resistance. The magnitude of frictional resistance depends upon the shape, size and condition of track and the velocity of train, etc. So let R be the specific train resistance in N per ton of the dead weight, and W is the dead weight in ton. Therefore, the tractive effort required to overcome the train resistance is given by W into N. Okay, tractive effort required to overcome the effect of gravity. What is the tractive effort required to overcome the effect of gravity is given by when the train is moving on upgradient, means it is upon moving uphill, the gravity component of dead weight opposes the motion of train in upward direction. In order to prevent this opposition, the tractive effort should be acting in upward direction to lift the train when it is climbing a hill. The tractive effort required to overcome the effect of gravity is given by Fn is equal to mg sin theta into n, that is 1000 into wg sin theta, where m is equal to 1000 w kg, 1000 w per kg. So gradient is equal to sin theta, that is equal to bc by ac, that is bc nothing but here elevation, and distance along the track is given by this formula, that is distance along the track, and gradient is equal to sin theta into 100. Percentage gradient is sin theta into 100. So when it is, this is a train moving on upgradient. So from the above equations, ft is equals to 9000 wg into g by 100, it gives you 98.1 wg1 gn, where g, capital G is there, and also here we will be putting the tractive effort equation as 98.1 wgn. So here we can take the positive as well as negative sign here. The positive sign of train is moving up gradient, and negative sign for train is moving in down gradient. This is due to the fact that when the train is moving on the up gradient, the tractive effort showing equal required to oppose the force due to gravitational force. But while going down the gradient, the same force will be added to the total tractive effort. So the total tractive effort required for propulsion of train is given by Ft is equals to Fa plus Fr plus or minus Fg. And also we will have this equation ft is equal to 27.7.8 wt alpha plus wr plus or minus 98.1 wgn. So talking about the specific energy consumption, the energy input to the motor is called as energy consumption. This is the energy consumed by the various parts of train for its propulsion. The energy drawn from the distribution system should be equal to the energy consumed by the various parts of the train and quantity of energy required for lighting, heating, control and braking. This quantity of energy consumed by various parts of train per ton per kilometer is known as specific energy consumption. As the name itself is given there, the specific energy consumption refers to each and every part of the traction train that is consuming the energy is called as specific energy consumption. It is expressed in watt hours per ton per kilometer. Specific energy consumption is equals to total energy consumption watt hour divided by the weight of train in tons into distance covered by the train in kilometers. Now we will see the determination of specific energy output from the simplified speed time curve. Energy output is the energy required for the propulsion of the train or vehicle, mainly for accelerating the rest to velocity Vm, which is energy required to overcome the gradient and track resistance to the motion. Now the energy required for accelerating the train from the rest to its crest speed is Vm. If you see this, the energy required for acceleration of train is equals to power into time, where power is equals to work done by time into time. Time gets cancelled here, and work done by time can be written as tractive effort into velocity into time also it can be written. Either you can directly say that work done is equal to energy here, or else you can say tractive effort into velocity into time also gives the energy, that is tractive effort is equal to ft into vm by 3600 into t newton kilometer per hour per second. So ft into 1 by 2 into vm by 3200 into t1 by 3600 newton kilometer will be the equation here. So we see that half into Vm square by 3600 whole square into alpha into Ft, where T1 is equals to Vm by alpha, and therefore we see that we are having the energy requirement here, and the energy required for accelerating the train is this much, half into Vm square by 3600 whole square into alpha into 277.8 We alpha plus 98.1 Wg plus Wr kilowatt hour. So energy required for overcoming the gradient and tracking resistance to motion. Energy required for overcoming the gradient and tracking resistance is given by tractive effort into velocity into time, that is ft dash into vm by 3600 into T2 by 3600 kilowatt hour. After simplifying, we get this equation Vm into T2 by 3600 whole square into Wr plus 98.1 Wg kilowatt hour. So where Ft is the tractive effort required to overcome the gradient and track resistance, and W is the dead weight of the train, R is the track resistance, and G is the percentage gradient. The total energy output is equal to energy required for acceleration plus energy required to overcome the gradient and resistance to motion. So when we fulfill this particular formula, so this particular formula, if you fulfill these things, whatever we discussed in the previous slides, so we came to know that it is Vm square into 1000 by 2 into 3600 whole square into alpha into 277.8 into We alpha plus 98.1 Wg plus Wr plus Vm into T2 into 1000 by 3600 into Wr plus 98.1 Wg watt hour. So here these formulas after simplification here we will get here this formula 0.01072 We Vm square plus 0.2778 Wr plus 98. Wg into d1 plus d2 watt hour. So here d1 and d2 are separate, that is d1 is equal to Vm square by 2 into 3600 is equal to Vm square by 7200 into alpha, and d2 is equals to Vm into T2 by 3600. The specific energy output is given by energy output in watt hour by weight of train in tons into distance running. So we can easily write this formula, and also we can discuss about the factors affecting the specific energy consumption. Factors affecting the specific energy consumption are as follow: the distance between the stations. From equation, specific energy consumption is inversely proportional to distance between the stations. Okay, that means that specific energy consumption is more, means the distance between stations is less. Now greater the distance between stops, the lesser specific energy consumption. The typical value of specific energy consumption is less for the main line service, that is 20 to 30 watt hour per ton per kilometer, and high for the urban and suburban service, that is 50 to 60 watt per hour per ton per kilometer. Now acceleration and retardation. For a given scheduled speed, the specific energy consumption will accordingly be less for more acceleration and retardation. The maximum speed for a given distance between the stops, the specific energy consumption increases with the increase in speed of the train. So it is clear that what is maximum speed. For given distance between the stops, the specific energy consumption increases with the increase in the speed of the train. And coming to this gradient and this particular thing, gradient, and also we will study about the definition here, that is the gradient one. So we have studied about the distance between the stations and acceleration, retardation, and maximum speed, and it is now gradient and train resistance. From the specific energy consumption, it is clear that both gradient and train resistance are proportional to specific energy consumption. Normally, the coefficient of adhesion will be affected by the running of train and the percentage gradient, conditions of track, etc. For wet and dry conditions, the value of coefficient of adhesion is much higher compared to dry and sandy conditions. So these things are to be kept in mind here, and some of the questions that are to be asked in these are explain the factors affecting the specific energy consumption, determine the specific energy output for simplified speed time curve, write about the mechanics of train movement, and write about the factors affecting the schedule of speed of the train, and explain the speed time and speed time curve and the distance curve for different services. So already we have discussed this part, and students, I would like to end my topic here. In the next class we will study about the different topic. So thank you.